Hello friends. This lecture continues special cases of econometrics applications, and today we will discuss a topic of a regression with a binary dependent variable. So far, we assumed that the dependent variable is continuous. We studied two cases. One was the long empirical exercise example about student to teacher ratio effects on the test scores. And we used a continuous variable, which was the district-wide average test score. Another one has been used during the panel data topic, and we spoke about traffic fatality rate. We can, in principle, observe such cases when the dependent variable is binary. For example, if you want to predict whether a person goes into the college or not, or if you want to estimate the effects of some determinants on this decision, whether a person decides to smoke or not, and what are the factors affecting this decision. Whether the mortgage application is accepted or not, and again some causal effects of different variables on this decision. In the machine learning, the similar task is called the binary classification problem. So you need to classify your object into one of two possible groups or classes. And in econometrics, our primary goal is to establish the causal relationship between some variable x and this binary dependent variable. In machine learning, we usually want to make some predictions to classify when some object with the unknown, which we don't know to which group it is attributed, where we need to classify it. For example, we want to predict whether email is spam or not, whether the person is, for example, whether we need to apply his mortgage application or not, and so on. For this lecture, we will be using the empirical example of the Boston Federal Home Mortgage Disclosure Act, which contains individual applications for mortgages made in 1990 in Boston area. In total, we have 2,380 observations collected under this act, and we are going to work with the following variables. So first of all, there is a dependent variable, which is binary, and it represents that the mortgage is denied, and the dependent variable equals 1 in this case, or accepted, 0. So basically, this is completely voluntarily choice whether you want to mark your dependent variable with 1 when the mortgage is denied, or with 1 when the mortgage is accepted. The interpretation changes, of course. The independent variables of interest are, first of all, we can understand that the decision about the mortgage application, whether we reject it or accept, depends on some economic characteristics of a person, of an applicant. Those are income, wealth of a person, employment status. There might be some other financial characteristics, like whether a person has another loan, some property characteristics if you apply for the mortgage, like district, market price, maybe some neighborhood, and so on. And one of potential determinants of this decision might be the race of an applicant. So we want to know whether there is some discrimination related to a race. Well, in principle, we can think about some gender discrimination, about some other thing. That's going to be also the variable of interest for us. This is an excerpt of from this data set. We have many different variables collected on the mortgage applications, and here in the red frame we have three variables that we have discussed. So deny is 0 when the mortgage is accepted, and 1 when the mortgage is denied. PI ratio is a fraction of a payment for this mortgage to the total income of a person. So in principle, if you pay more out of your income, this is more difficult for you to maintain this loan, and most probably your application is going to be rejected. So we expect that the higher is this PI ratio, let's say PI ratio on average is higher for those applications that has been denied. And binary variable black, which is 0 for non-black persons and 1 for black persons, for black applicants. Given this data, the most natural starting point for us is to apply what we already know, linear regression model with a single regressor. So we take this model and suppose that y is that binary dependent variable deny, and x is payment to income ratio, PI ratio. Now the most important question, once we have this model, how to interpret beta 1 when y is binary. Because you remember that usually beta 1 has the following interpretation: it is the partial derivative of y with respect to x. But now y is not continuous, y is discrete, and we are not able to take this derivative, and the meaning changes in the same way as in the case when x was binary. Next question, what does this line mean if y is binary? If y is binary, technically there is no line, because y has only two levels, either 0 or 1, and line is continuous. How this interpretation changes? What does the predicted value mean when y is binary? For example, if we plug something into this estimated regression line and we get 0.26, what does this mean? So we need to answer these questions, and we start with the following thing. We all remember that assumption 1 for OLS says that the expected value of an error term conditional on x is 0. If we try to express the conditional expectation of y given x, we arrive to the population regression line expression. Now, on the other hand, we do the following. When y is binary, we in principle are able to write down what is the expectation of y with the help of probabilities. When y is 1, there is some probability that y equals 1, and y is 0, there is some probability that y is 0. So expected value of y equals to the probability of y equals 1. Looking at the left hand side expressions, we see that, well, this is conditional probability, this is unconditional probability, but in principle we can also state this as a conditional probability, conditional on x. And looking on the right hand side expressions, we can write down the following equation, that conditional expectation of y given x equals to the conditional probability of y equals 1 given x. So if I know x, what is the probability that y equals 1? This is exactly the expected value of y when y is a binary variable. And this answers most of the following questions. When y is a binary, the linear regression model is called the linear probability model. We are trying to capture the probability of y when we know something about x. And as we said, the expected value of y is a conditional probability. Well, expected value of y given x is the probability that y equals 1 given x, and this is the probability that y equals 1 given that x equals some value. Y hat is now the predicted probability that y equals 1 given x. And beta 1 is the change in probability for a given delta x. So if x changes, how much probability that y equals 1 changes? Now, when we estimate this model on the data discussed on the one of the previous slides, we have the following model. So deny, which is binary variable 1 or 0, equals to the following expression, minus 0.08 plus 0.604 times payment to income ratio. What is the interpretation? Let's see. What is the predicted value if PI ratio is 0.3? We just plug this value and we compute that probability of a denial when PI ratio is 0.3 is around 10%, 10.1%. When predicted value, when PI ratio is 0.4, so 40% of your income goes as a payment for the mortgage, probability of denial logically increases. So it's 16.2%. So the marginal change in probability of denial is 6.1% when the PI ratio increases from 0.3 to 0.4. When we extend this model with the binary variable black, what do we have? We have the following estimated model, so single coefficient hypothesis all rejected at the 1% significance level. So all coefficients are statistically significant. Therefore, we can work with them and we can give them some interpretation. So now let's fix PI ratio at the given level, for example, 0.3, and now let's compare probability of a denial for non-black person and for a black applicant. So for a black applicant, we plug PI ratio 0.3 on this place, and black as a binary variable 1 is here. So basically the slope of the intercept of a model changes. We have 25.5% probability that black person with PI ratio of 0.3 will not be granted a mortgage. Once we do the same for non-black applicant, we see that only 7.7% chance that a person, non-black person with PI ratio of 0.3 her application is going to be rejected. So the difference is 17.8 percentage points, and this difference is statistically significant. So it gives us a first baseline result that probably black applicants are in some sense discriminated. But of course, we didn't count for many important characteristics that might lead to the emitted variable bias. Right? So we need to control for these potential characteristics. Now, as the summary of what is special about linear regression model in the case when the dependent variable is binary. So first of all, because it's a linear regression model, it models probability as a linear function of x. So probability linearly changes with equal changes in x. It's simple to estimate. We know techniques how to estimate this, and the interpretation is very obvious. The problematic part is that error terms are gonna be large in the middle of x and small at the extreme values. We will see this on the illustration later. So which means that there is a heteroscedasticity. Okay, maybe that's not a big deal. We know how to control for heteroscedasticity. On the other hand, heteroscedasticity usually leads to lower efficiency of our estimation. And more important problem with this model that it is able to generate such predictions of probability that are greater than 1 and less than 0. And we are somehow confused. Probabilities cannot be cannot extend 1 and cannot be less than 0. So how to interpret such results? For our empirical exercise, we see that the regression line goes like this, and it crosses 0, and it goes into the negative area. For example, when PI ratio is 0.1, our estimated linear regression or linear probability model will predict negative probability of denial. Not a good result. Regarding the heteroscedasticity, again, you can see that in the middle, the distance between y and this line is the largest possible. When x is closer to extremes, either to the left or to the right, the errors are reducing. And that's exactly the case of heteroscedasticity. With the help of x, you can predict the spread of error terms. Well, the last point here gives us an idea to think about more appropriate models to capture this relationship and to somehow capture probability into the correct interval. And this is done with the help of two models. First one is called Probit and the second one is called Logit. So let's see. The problem with the linear probability model is that this model, so first of all, this model assumes that the relationship between x and probability is linear, and second, it extends over the limits, over the logical limits of probability. Well, we want this conditional probability to be bounded between 0 and 1 for all x's. And we want, of course, to have this probability increasing in x. So, which means that when x increases, probability also increases. If you think about the appropriate functional forms for this relationship, you might immediately recall such object which is appropriate for this case. So which function takes values between 0 and 1? Well, we know that from probability course that this is a cumulative distribution function. Well, cumulative distribution function is bounded between 0 and 1, and it is non-decreasing in x. Well, when x is continuous, it is decreasing. It is increasing, sorry. And in econometrics, we have two popular cumulative distribution functions. So first one is a standard normal CDF, and this is related to the Probit regression. And the second one is the logistic CDF, which is related to the Logit regression. So we start with the Probit regression. How the Probit regression works, what are the mechanics of this model? So it models the probability that y equals 1 using the cumulative standard normal distribution function evaluated at the following point. So we use an standardized random variable z, which is a linear function of x. And then we evaluate cumulative CDF of a normal distribution at this point. So basically, probability that y equals 1 given x is going to be a function, cumulative distribution function of a standard normal distribution evaluated at this linear function of x. Well, phi is the cumulative normal distribution function, and z is the familiar z value. We spoke about that z value during statistics course, during probability course. This is the standardized random variable with mean 0 and variance 1. So it is z value, z index of the Probit model. How, just as a reminder, how can we find z? If we know z, how we can compute this function or evaluate this function at a given value of z. In Excel, we are using the following function, norm.s.dist, and don't forget to put that this is integral function, cumulative function. And in Python, we usually apply the following function from a library stats. This is an illustration what Probit model does. You see that now Probit model and the regression function fits the data points better. So first of all, it is bounded between 0 and 1. Second, it is not linear. You see that there is faster jump from 0 to 1 in the middle, and it slows down closer to these asymptotes. When we estimate this model, I'm not going to discuss the exact technicalities of estimation of Logit and Probit here. So assume that we estimated them with the help of a Probit function in Python. We get the following coefficients. Now, the more important thing is how to interpret these coefficients and how to work with them in the same fashion as we did for the linear probability model. Well, we have the following estimated Probit function. Both coefficients are also statistically significant. We can do the same exercise as we did for the linear probability model. So first of all, there is a positive coefficient. If there is a positive coefficient, increase in PI ratio increases the probability of a denial, which is sensible. So standard errors have usual interpretation, which gives us a chance to interpret and to make the same hypothesis tests as we did for OLS. Now, how we can evaluate the predicted value for PI ratio? We plug 0.3 here, and then we have Z index or Z value inside of the standard normal CDF, evaluated and get 9.6. When we change PI ratio to 0.4, we just change this value here, and the result is 15.7. So compare this result with the previous result in the linear probability model. We had something like 10.1, 16.2, so it was 6.1% increase. Now we have almost the same 6.1% increase, but the values of probabilities slightly differ. So if PI ratio increases from 0.3 to 0.4, probability of a denial increases by 6.1%. What happens if we introduce a binary variable black into the regression? Again, we estimate the model, we extract the coefficients, all coefficients are statistically significant, and then we can fix PI ratio on the level of 0.3 and compare two probabilities. Probability of a denial for a black applicant, computed here 23.3%, and probability of a denial for a non-black applicant, which is 7.5%. So we see that once a person with the same payment to income ratio, but who is different by race, so the probability changes by 15.8%. Another model that is used in econometrics for this binary dependent variable case is called Logit. Instead of standard normal CDF, we have a logistic CDF evaluated at the same Z value. So instead of phi, I'm using just latent f here, and this latent f stands for the cumulative logistic distribution function. This logistic distribution function looks as follows, following. Logit is a popular model for classification and machine learning tasks. Why? Because it doesn't put any assumption on the structural form of a probability. So what is the, let's say, disadvantage of a previous model of a Probit, that we assume that there is a normally distributed variable. Now we don't put this assumption here, and you will see that without any assumption we can get, well, only one assumption is needed, that Z is linearly dependent on X, and using only this assumption we can build this logistic distribution function. So that's why it's popular in machine learning, and we have covered in the end of mathematical statistics course two other binary classification models. One was k nearest neighbors, another one was the naive Bayes classification. You see that Logit almost coincides with Probit, so that's why both models are more or less interchangeable, but as I said, Logit puts less structural assumptions on the data. So how can we derive a logistic CDF? We start with the definition of a following measure, which is odds ratio. We take probability that y equals 1, divide this by the probability that y equals 0, or 1 minus p. So this odds ratio, we are using this odds ratio every time. So suppose that p is 75%, then, and this is the probability that a person is going to be, the person's application is going to be rejected, 75%. So the complementary probability is 25%. When you divide 75 by 25, you get something like 3 to 1. So, and we are usually use this 3 to 1 chance that your application is going to be rejected. Or when you are thinking about your beloved football team, and the chances that they are going to win. And you can also say something like, well, there is 20 to 1 that they are gonna win, which means that there is a probability of how much, 20 over 21 that they will win, and 1 over 21 that they will lose. If the probability is bounded between 0 and 1, this odds ratio is bounded between 0 and infinity, which is again natural and logical. You can think about this. So when p is close to 0, it's 0. When p goes to 1, the whole fraction goes to infinity. This is the first step to create an unbounded variable. The second step is the following. If you take a logarithm of this variable, and this variable is non-negative, we are able in principle to take the logarithm. So the only case when the logarithm, when this fraction is 0. But when the fraction is 0, the log goes to the minus infinity. And in total, this log is unbounded. It is from minus infinity to plus infinity. And now we know that the familiar linear regression model is also, when the variable is continuous, is also unbounded. So now we can say, well, what if we, on the right hand side, put a linear regression line, but as the dependent variable, we are not gonna use this binary variable, which is y equals 1 or y equals 0, but rather we are using this variable, log of odds ratio. Now it is possible to estimate this model and interpret this model with the help of OLS. And you see that we didn't put any structural assumption here, just an assumption of linearity in axis. And now how to construct the logistic function? We need to convert everything back. First of all, we unlog this variable, which means that we take an exponents of a left-hand side and right-hand side. On the right-hand side, we get the following thing. Now we multiply left and right-hand side by 1 minus p. It's here. And the next step, we open these brackets and move the term with pi to the left, which is here, with p to the left. We factor p out. Finally, we have the following thing, and now we can express p here. So the last step is just to divide both numerator and denominator by e to the power of this linear function, which is here, and this is the familiar logistic CDF that we have introduced 2 slides before. Now, once we estimate this logistic function, we get the following coefficients. So the coefficients are not directly comparable to those of Probit or to those of linear probability model. So don't try to compare coefficients of different models. They are not comparable at all. So what you are able to compare is the interpretation of the results, the predicted variables. For example, when we are using Logit for black person with PI ratio of 0.3, we get the following probability, 22.4%. When there is a non-black person, we have 7.5%, and Logit says that there is a difference of 14.9%, that a black person is not going to be granted a loan compared to a non-black person. So the probability differs by 14.9%. You see that all 3 models technically gave almost the same result regarding this causal effect, but if you look into other intervals for PI ratio, the results are going to be much more different. A very short note on the estimation. This is not an, let's say, the most important idea of this lecture, rather some technical case for those who want to understand how the estimation is done. So both Probit and Logit are nonlinear functions of the coefficients, which means that we cannot estimate coefficients beta 0, beta 1 to beta k with the help of OLS. It is not possible. But we know other estimators from mathematical statistics course, and two most important of them are method of moments estimator and maximum likelihood estimator. So since we know the functional form of CDF for both models, we can apply the method of maximum likelihood to both models to estimate these betas. And going back to the estimation results from Python, you can see that it explicitly says the method of estimation is MLE, while for the linear probability model, when we see the outcome from Python, it says that the method of estimation is least squares. So method of maximum likelihood is applied to find such values of estimators beta 0, beta 1, beta 2, and so on heads to maximize the likelihood of observing this exact collected data set. So technical details are not discussed here, just for you to understand that the estimation procedure is different. And those who are interested can look at the appendix 11.2 from Stock and Watson book. So to conclude, when y is binary, the interpretation of a regression function is the conditional probability that y equals 1 given values of x. We have discussed three models. One is linear probability model, where we apply a usual linear multiple regression. Another one is Probit, which is based on the cumulative standard normal distribution. And the third one is Logit, which is based on the cumulative logistic distribution function. All three models produce predicted probabilities, and when x changes, the interpretation is that there is a conditional probability that y equals 1 changes because of that. So the causal effects are interpreted in a way that change in x leads to the change in probability that y equals 1. And yes, for nonlinear variables, this causal effect depends on the initial level of x. For the linear probability model, it is not the case. So this is all for this topic. Thanks for your attention and see you later.